Hello, everyone, and welcome to Road to Reason, A Skeptic's Guide to the 21st Century. My name is Rick Wingrove.
And I'm Larry Mendoza.
And with us today is Dr. Harold Geller of George Mason University. He is an associate professor in the George Mason Physics, Astronomy, and Computational Sciences Department, and the observatory director for what I didn't know, that there is actually a working observatory at George Mason University.
Yep, right on campus in Fairfax.
32-inch.
32-inch diameter Ritchie Accretion.
Yeah, great.
Nice facility.
We'll talk about that.
Everyone's welcome to the, we have public events twice a month.
We'll talk about that some more.
Good.
We're doing first some announcements.
Yeah, let's do some announcements. First of all, I want to remind our audience today is the last day to vote for our show. There's the graphic there you can see. Go to Fairfax Public Access TV on the website there and click for our show. Vote. Today's the last day. We're competing with another TV show that airs on the same channel, and we'd like to win this. So remember to go on there and vote. Another announcement: we still need some help with the show. If you'd like to donate some money, there's you can write a check to Fairfax Public Access with that address, and attention to Paul Sheehan, who's our producer and does a wonderful job. But we can make the show better, and the only way to do that is if you guys help us out. And also, if you would like to get into the TV business and want to learn about running a TV show, doing some production work, maybe even host, you can always come in and sign up in Fairfax Public Access. They got free classes. Some classes are not free, but you can get a discount if you volunteer. So if you want to help us out in the show, make it better, come on by.
Okay.
So
was that all of it? Oh, we're also a lot of male hosts around here. We're looking for one or more female hosts to join us occasionally. So
we like diversity.
We do like diversity. So, okay, we're going to start today with just a little bit of sad news. Edwin Kagan, if you don't know who he was, is the National Legal Director for American Atheists. Died 2 days ago. Ed Kagan, besides being the National Legal Director for American Atheists, was also the founder of Camp Quest, which, if you don't know what that is the a camp for secular and atheist children. The picture you're seeing right now is Edwin doing one of his famous debaptisms. That's a hairdryer. He does debaptisms at the atheist conferences. And he was a hell of a man and worked like a dog for the atheist cause, and has been a member of the bar of the Supreme Court of the United States since 1975. He is survived by 4 children, 5 grandchildren. His wife Helen was died in 2010 and was also a big loss to the atheist community. Edwin was currently involved with the World Trade Center case in New York City, and also American Atheists had, we've talked about it on the show, sued the IRS over unequal privileges, special privileges given to religious organizations in 501c3s, and he was, big part of that case. So he will be missed. Those who knew him, I counted him as a friend, and he was helpful to me in a lot of ways, and was just a powerhouse. I'm frankly amazed he lived as long as he did, because he was a hard worker. Bit of a curmudgeon, I think some people thought, but he was a brilliant guy, a real wit. He had a book called Baubles of Blasphemy, which is his own poetry and observations. And if you want to know how much of a scoundrel he was, go to his website and look what his mailing address was in Union, Kentucky. Was Post Office Box 666. So, Edwin, we miss you. You will be missed. So.
Yeah, we will. He was a great man. I had a pleasure meeting him, and it was very sad news and
huge loss.
Huge loss. So our thoughts go out to his family and friends, and
and to the atheist community in general.
Atheist community, correct.
So, what else you got?
So another little bit happier news. I want to announce here Neil Shubin, who is an evolutionary biologist and a paleontologist, wrote a book called Your Inner Fish. And on April 9th, they're going to start off on PBS a 3-part series called Your Inner Fish, based off of this man's book. And Your Inner Fish is basically the story of Tiktaalik. And Neil Shubin discovered Tiktaalik. He's a professor at the University of Chicago, and went out and was looking for transitional fossils. He found one. Now, Tiktaalik is a transitional fossil from fish to land animals. It actually had a neck bone. It had flippers, which had basically 2 bones and actual digits. So it was a huge find. And so Howard Hughes Medical Institute, Sean Carroll, who's the vice president for science education, started a TV production company called Tangled Bank Studios. And this is going to be their first full-length TV show that's going to air on PBS on April 9th. So I urge everybody to go read the book, for one, but also watch the show April 9th.
Yeah, I agree. I just bought a Kindle recently, and one of the first books I picked up was Neil Shubin's Your Inner Fish. And it was fascinating. I read pretty much straight through it.
Yeah, it's a great book.
He describes pretty much that our inner fish is not some kind of metaphor. There's a direct line. The Tiktaalik, interesting thing I was just mentioning, was that is the first one we've seen. First of all, this is a fish with feet. This is a real Darwin fish. It could push up, it could climb up out of the water, it could breathe air. Its nostrils were on top of its head. Its head was already evolved to look like an alligator. But it, very importantly, its structure of its limbs was 1 bone, 2 bones, a bunch of bones, and digits. And it was the first one that had them, and everything in that line coming to us has the same pattern. It is amazing, amazing book.
So he also, by the way, has another book called The Universe Within, which he talks about how we are not only directly related to these fish ancestors of ours, but also he takes it even further in how we are actually made up of star stuff. You know? We are basically part of the universe, and every atom in our body is part of the universe.
And just speaking of the universe.
Yes, speaking of that.
Our guest today, as I mentioned, Dr. Harold Geller of George Mason. Among other things, Dr. Geller is the author of this book, which is, what is it? All the Secrets of the Solar System in large print. And you have another book coming out too very soon. What is that?
Yeah, within a month or two, similar to that, All the Secrets of the Universe in large print also. And whereas this book has no illustrations, I did get an illustrator, and I hope it'll be for the general public and also for people a little hard of seeing. So good large print.
These are available as ebooks and online.
Yes.
So,
Yep, we urge everybody to go pick up these books and read all about the solar system, the universe.
But the main reason we got in touch with you to get you on here was the recent news about the Big Bang, the background radiation, and the implications of that.
Yes,
so
and
if you
I
want to
do
elaborate.
want to point out that the findings that were announced have not yet been published. So it has not gone through the peer review process. You haven't had the opportunity for scientists to review the data that this Harvard team has put forward. Certainly not questioning what they conclude, but you really can't know exactly what's going on until you see the properly published paper that has gone through the peer review process.
But it's not published yet, so there's always potential for disaster in a situation like that, to be premature in these things. But they said that it's sigma 5 or 6 level of certainty, which is, you might want to explain that, what that means.
Sure, well this just has to do with, there's always some kind of spread in the data. Nothing is ultimately or infinitely precise. And so you look at, just like in my astronomy classes, we have exams and we have a spread of the grades. You know, the average may be somewhere in the 70s with a certain spread, and then that sigma is the standard deviation. So the question is, well, all of the class scored within a certain region, and if you're looking at data that overlaps too much, that's still within the error that you may have. But when you get certain numbers of standard deviations away from the median of that data set, then you can confidently say, well, that's too independent and that it's not showing something from that other set or group.
Okay.
So yeah, again, I mean, it may well be proper what they've said, but I do want to point out that it has not been through the peer review process and it hasn't been published quite yet.
Just tiptoeing past the fact that it hadn't been published yet, the implications of it, if it is verified, and it's not really inconsistent with anything that we've seen before, but if it is verified, peer-reviewed, and published, it's kind of a big deal what they've discovered.
Well, what they've really discovered is a signal that is indicative of two things. One, inflation itself. The cosmic microwave background radiation has been available to us since even the 60s. Penzias and Wilson won a Nobel Prize for the original data, and more recently, I believe 2006, John Mather and George Smoot won for their data set with the cosmic microwave background radiation. And even a little later, the Wilkinson Microwave Anisotropy Program satellite had acquired higher resolution. But here what they did is have a specific type of cosmic microwave background radiation that they're looking for, that it's polarized. I guess an example would be you have polarized sunglasses. And so, you know, sometimes if it goes through a certain direction, if it's polarized one way, then it blocks the light and you don't have that kind of radiation coming through to the eyes. And if it's polarized in the other way, it actually can pass through.
Right.
So you're looking for a signal. That's one of the things that's different about this experiment, that the polarization of the signal in the cosmic microwave background radiation. And that gives you an idea also of being able to look for very, very fine differences. Even with the COBE satellite, that's the Cosmic Background Explorer that NASA launched in 1989 that ultimately led to the Nobel Prize in Physics for John Mather and George Smoot in 2006. Those data are go down to millikelvin temperature differences.
Right.
But here we want to look again, not just the temperature differences, but the polarization of the electromagnetic radiation coming from that region.
And there are also some indicators of the spin of these too on the diagrams that were published.
Well, that really goes to the polarization. In essence, you know, an electromagnetic wave is an electric field, a magnetic field, and then the direction of the wave itself. And so, yes, you can tell left-handed, right-handed, that goes
Right,
to polarization.
yeah.
And another aspect here that's important is the fact that if they are correct in what they're saying, it goes to two things. One, it's data that supports the inflation theory that was first put forward by Alan Guth in 79-80. And that's one of the differences, that you can actually see the fingerprint, in a sense, of the inflation. And the other thing is that it would also be indicative of gravitational waves that were predicted just about 100 years ago by Albert Einstein. I believe the paper was originally published in 1915 in German, but then in English didn't get out until 1916 because there was a little war going on at the time that kind of took a while to get that out. So the best example that I know of how to use is one, as far as the difference in polarization of the signal, can tell you that there was an expansion. Again, the cosmic microwave background radiation is indicative of the Big Bang model. We usually say that there's three different pieces of evidence that very much support the Big Bang. One was the expansion of the universe discovered by Hubble back in the 20s. The other one is the cosmic microwave background radiation, first discovered by Penzias and Wilson in the 60s. And the third is the abundance of chemical elements in the universe, how they are today and how they were in the past. And I get from my students, a lot of people are curious, well, how can you tell with the abundance of chemical elements in the past? People forget when you look out into space, even with our own telescope at Mason, when you look out into space, you're looking back into time.
Back into time.
So when you take the spectral fingerprints of the elements from stars and galaxies more distant, you're going back in time. And so you can say those galaxies that are so far away, billions of light years distant,
Right.
then you're actually seeing the chemical fingerprints from billions of years ago.
Sure.
So you get a better idea of the changes that have taken place over time. Those are the three main pieces of evidence. But none of those really address the inflationary epoch that was predicted by Alan Guth. And what you have is the sort of wrinkles that gravitational waves would put into our space-time continuum. Because of inflation, they get expanded very rapidly. People get really upset. People saying that, gee, it expanded greater than the speed of light. But please remember, there were no photons or matter at the time.
Right.
It's space-time expanding at faster than the speed of light. That doesn't violate special relativity or anything, because you don't have the photons, quarks, and other electrons and
Or
particles in
space.
existence yet.
Yeah.
That's right. You're starting with nothing. It's something that is hard to get across. You start with no matter whatsoever. It is simply energy of the
Right.
universe.
Right.
And so because of the inflationary epoch, which this is, if valid, is giving demonstration of, then the gravitational waves that are extremely difficult to see get stretched out very quickly, and it's actually able to make them out. So this would be indirect evidence of gravitational waves. We have some other indirect evidence, no direct evidences yet, but this would be additional indirect evidence of gravitational waves.
No, it was
So that's interesting. And earlier there was a image about how the Big Bang kind of started, and there it is again.
Yeah.
Oh, okay.
So that's not quite a correct image, I would imagine. These images here. Can you maybe talk a little
No,
bit
if we
about?
can go back to the first one, which has
Yep.
been out quite a
Yep.
bit. And that's actually, this one was produced by, as you see, WMAP is the Wilkinson Microwave Anisotropy Program satellite. And I think it does sometimes confuse people. That's not what we're saying the shape of the universe is.
Right.
Remember, again, you're starting from nothing, and then it has expanded in the inflationary epoch exponentially. And what that diagram was showing is the horizontal axis is really representing time. And so the cone at the end really represents the size of the today's observable universe. And you're starting really from nothing, which is sort of difficult to demonstrate, but then expanding very quickly and then going out. And the vertical axis here, again, is the size, and the horizontal axis is time. So it's not the shape of the universe. In my classes, I prefer to use a balloon model. And so if you take a balloon and start blowing it up, that's giving you an idea. Now, the difference here is that you're limited to the surface of the balloon.
Sure.
So first of all, you can't say there's a center to that universe because you are limited to the surface. You can't point down or up.
Right.
There's left, right, back, forward, but no down or up in a two-dimensional universe. And that balloon, if you keep blowing it up, gets larger and larger in size. And what we're saying is in the very early period, and we're talking about 10 to the minus 36 seconds after the formation of the universe, that's very, people say, how small is that? Well, 10 to the minus 12 is a nanosecond, and so that's, one nano would still be 1/24th. That's 10 to the minus 36 seconds afterwards.
It's
Very
essentially
quickly it
just
expands fast.
Instantaneous. Yeah. I mean.
And then it continues to expand. So again, those diagrams aren't showing you the shape or size, but it's trying to give you an idea of the size of the universe over time, which they use the the horizontal axis. I should
Yeah,
say.
looking at that diagram, it is confusing, to try to visualize the extra dimensionality that's trying to show us there, and it's easy to think of things as having edges. And it raises the question, when we look out at like the Hubble Deep Field and we see a galaxy that's something like 11.5 or 12 billion light years distant, if you're on a planet in that galaxy, what are you looking at out there?
Well, this goes to what's called the homogeneity and isotropy of the universe. Homogeneity refers to wherever you are in the universe, it looks pretty much the same. So actually, if you were on that galaxy far away from us, you would still see the universe pretty much the way we see it.
Still 13
Not the
billion
same,
light years in all
exactly.
directions.
Yeah, and it's hard to think that way and get that across, but as I said, you're getting the light from that galaxy about 13 billion
Yeah.
years. Now, the cosmic microwave background radiation comes to us at a time that's about 386,000 years after the formation of the universe.
And is
and
that
you
what
cannot see beyond that because of the nature of the universe at that
Right.
time.
Is that when the diagrams they put out with the polarization and everything, is that the inflation we're looking at there, or is that 380,000 years later?
The figures that they'll be putting out relate to the cosmic microwave background radiation, but very small differences and also polarization in the signals from the most distant regions of our universe. Okay? And it's the changes that they have examined, apparently, that do provide evidence that there was a period of expansion. And because you have this inflationary epoch and period of expansion, you're able to make out the gravitational waves, which are very difficult to see.
Right.
In fact, people use waves in so many different applications, it gets a little difficult to get the point across. Just recently, there was a discussion of waves on the surface of some of the lakes of Titan, the moon that orbits Saturn. And then when you read the article, which just came out last week, the guy was talking about 1 millimeter waves. Now, I don't know about you, but I don't know that I call that. It's nothing you can surf on or anything. But you're talking about, 1 millimeter waves, that's it. Because there's also the issue with the lakes and oceans on Titan are made of methane and ethane. They are not water.
Not water,
Right.
right?
And very different. And here on Earth, we keep forgetting, we think of everything in terms of water, but water freezes from the top down. But these other chemical molecules, they freeze from the bottom up. And that's why you get this guy writing about waves on the surface of Titan that are just 1 millimeter. I mean, that's like nothing, of course.
Sure,
You can hardly see that. But yet, some of these astronomers are referring to them as waves. And that's very different than the waves that we're talking about in the cosmic microwave background radiation that you would see. But that's the analogy that they're trying to give you.
I see.
Well,
That's very, that's quite an interesting find. So when do you expect the paper to be published? Do you know?
Oh, I'm not privy to that. Many of my colleagues don't know also. I mean, we suspect it will be coming out within the next few weeks, or even if there are some issues with the calculations, it may be a couple of months still. They sort of jumped the gun, but I think they're, they have something that will be spectacular, but they were a little eager to get the information out there.
the polarization and the gravity waves, the ability to detect these very subtle waves, I read it also has implications for the existence of gravitons. It seems to support.
Oh, yes.
that they are.
Well, both were predicted by Einstein's general theory of relativity, so it kind of goes hand in hand. And
But so far we
mention that.
have no hint. We've never detected any.
Oh, we have indirect evidence
of the gravitons?
gravitational waves and existence of gravitons, indirect evidence. And this would just be more supportive evidence.
Right.
It's just very difficult, and I'm afraid one of the missions that NASA had that was going to look for gravitational waves and the like was defunded, or not funded, but very difficult. You're talking about the limits of our technology.
I know there are some ground-based things with two long legs, which are supposed to be able to. They're designed to be able to detect gravity waves, but so far I don't know if they have any positive.
No, again, there's still no direct evidence.
And then I don't know if this satellite group is up, but there was at least talk of a long baseline satellite cluster, 3 satellites with like a 1 million mile baseline.
Yeah,
or
that's
something.
called interferometry.
Yeah.
And again, that was not funded. Hopefully, sometime in the future, we'll get to do some direct measurements of gravitational waves.
Right, and that
It's
was
very difficult.
pretty much the missing piece, that everybody's looking for, the gravitational waves and
gravitons, quanta themselves.
Right. So that's that's interesting. It's looks like we're moving. As science predicts, and Einstein predicted, and now we're getting more and more evidence.
This might be a good time to take a break. So we'll do that, and we'll be back in a couple of minutes.
Welcome to Student News with the Secular Student Alliance. I'm Liz Liddell, the Director of Campus Organizing, and I'm here to share some of the most exciting news and events happening on high school and college campuses across the country. We have some exciting news to get us started off this week. The administration at Aberdeen Central High School in South Dakota has responded to our efforts to support the secular student group forming at the school. While the group was originally denied, the administration was highly responsive to our communications, recognized their error, and has confirmed that the group will be included in the Aberdeen Central High School community. We are always excited to see administrators owning up to mistakes and correcting these situations, and so we applaud the Aberdeen administrators for their response. In another piece of exciting news, we're delighted to announce that the National Secular Student Alliance is welcoming Jamila Bey as our new communications director. Jamila's extensive experience with NPR, journalistic writing, and public speaking will bring a fresh perspective to communications efforts not just for the national organization, but for secular students across the country. We're just a few days into the spring season, which is a great season for student-hosted conferences. 3 major events are coming up in the next few weeks, including SkepTech 2 at the University of Minnesota, Reason Fest at the University of Kansas, and the Free Thought Festival at the University of Wisconsin-Madison. All 3 events, hosted by Secular Student Alliance affiliate groups, are free and open to the public. You can always learn more about secular students and their work on our website at secularstudents.org. This has been Student News with the Secular Student Alliance. I'm Liz Liddell, and I'll see you next time.
This is Richard Dawkins. Doing commercials is unfamiliar territory for me, but I'm inviting you to watch Road to Reason, a skeptic's guide to the 21st century, on Fairfax Public Access every Sunday. Each week the hosts tackle wishful thinking, religion, pseudoscience, and the harm they cause, with a combination of facts, humor, and community involvement. They challenge believers to defend their faith and give you, the skeptic, a voice. With live call-ins for viewers and streaming on the World Wide Web, there's never a dull moment. Don't wait. Look at them now on Facebook and YouTube, and remember to watch Road to Reason, a skeptic's guide to the 21st century, or there'll be hell to pay.
Okay, now we're really back. And again, with us today is Associate Professor at George Mason University, Dr. Harold Geller. We're talking about the recent information that came out about the Big Bang, but also other astronomical subjects and existential stuff. So you have a really nice telescope over at the observatory, and you said you actually have proven ability with that telescope to detect extrasolar planets?
Yes, we do. Using a similar method that the Kepler mission that has discovered a few thousand, well, they've provided a few thousand candidates for stars that have planets orbiting. We demonstrated that at our observatory on the Fairfax campus of George Mason University. We were able to demonstrate the existence of a planet orbiting a star distant. It's much larger. You're not talking about Earth size, something that's a few times the size of Jupiter. Obviously, if you're out in space, you can do a lot better. But yes, we do have supportive evidence of an extrasolar planet around a particular star, and able to do that there.
Well, once that dam broke, it's just, they're just thousands, or have we hit 1,000 yet? There's
yes,
a lot of
we've gone
planets.
well over 1,000 at this point. And it almost increases daily. I actually often put notes. I have a Twitter. I Twitter as AstroBioProf.
AstroBioProf?
Yeah, AstroBioProf. And I started that because of course, I teach in astrobiology, and so I'll often make note of the number that we've ratcheted up, the number of planets orbiting other stars that we've detected.
So let's talk a little bit about astrobiology. What exactly is that for our audience? What do you?
Well, I define astrobiology as the study of the origin, development, distribution, and search for life in the universe. Made up a little acronym, and if you looked at that, you'd see ODDS, which, what are the odds? The odds, and that's astrobiology. So one of the key things that is done by astrobiologists today is looking for planets around other stars, and in particular trying to find a planet in what's called the habitability zone around a star, which is really just defined as that region around a star that allows you to have liquid water on the surface. So you're looking 0 to 100 Celsius on the surface in that region based upon the temperature of the planet.
Yeah, no, that's interesting because life as we know it is based off of water, right? But in watching I don't know if the new Cosmos series with Neil deGrasse Tyson, he actually made a comment mentioning that there may be other types of life forms out there that are maybe based off of different types of
silicon or
something.
petroleum.
Like that. Yeah.
There are, not to disagree, but when I discuss this with my class, I do point out, first I would say life is based on carbon chemistry.
Carbon chemistry.
Carbon chemistry. Water is important. That's used as the medium within all of the cells to transfer and conduct your metabolism. But basically, we're carbon creatures. And some say, well, why can't you have something else? Just look at the the abundance of chemical elements in the universe. Based upon what you had said earlier, it's all star stuff.
Right.
And I'm afraid, even if you want to have these dreamy creatures made of silicon, there just isn't as much silicon as there is carbon.
Sure.
Okay, there's an enormous amount of carbon. I don't want to misquote here, but carbon is like the third or fourth most abundant chemical element in the universe. Part of the reason because it's made by stars. Okay,
Right.
It's easily made by
And
stars.
that's right. More easily made. The lower mass stars
Yeah.
always get to at least carbon.
Right.
You need a much more massive star to get beyond that in the chemical elements.
And I forget the sequence after helium. It's what then?
Well, you go
lithium
hydrogen
or something?
fusion to
Right.
helium. Helium fusion goes to carbon.
Okay, strictly the carbon after
Then,
that.
yeah, and then it gets to neon, silicon, and ultimately iron.
Yeah, and that's the end of
Okay.
the star right there.
That's the end of the fusion process.
Right.
When you have iron in the core of a very massive star, you cannot get energy produced in that core. So what happens is the star begins to collapse.
On itself.
And applying Newton's third law of for every action there's an equal and opposite reaction, very simplistically put, once you have this contraction of all the outer layers, there's a rebound. It's like a bounce, and that's your supernova explosion.
And that all happens very quickly,
Yes, it
too.
does.
Yeah.
Very quickly.
And following that, I'm sorry, I keep stepping all over you. Following
ahead.
shortly after that, you end up with these exotic dwarf entities, white dwarfs, magnetars, pulsars.
Well, only white dwarfs are produced by solar mass type stars like our sun. They end up as white dwarfs. If you go beyond about 3 solar masses, then those will produce either a neutron star or a black hole. Some of those others that you talked about are really just types of neutron stars or black holes.
Right, with just incredible amounts of gravity and magnetism and everything.
Well, what do you say? I mean, if you substituted a black hole with the mass of the sun at the center of our solar system, the effect would still keep everything in place.
Yeah, we'd
So
continue
there's no-
our same orbit.
Yes,
yeah.
that's right. So it wouldn't be any change there. But
Right.
you have this explosion which blows everything
Blows
Yeah,
everything
right.
away. And that's a true explosion, which also is different than the Big Bang. A lot of people mistake the Big Bang for a type of explosion.
Right.
Remember, there is nothing else. Space-time itself is expanding. It's not matter within space-time that's blowing up.
Yeah.
And so it's really very different.
So that's interesting because people do have a hard time grasping this concept of nothing before anything. And of course, a lot of religious people will start to say, well, there was a creator that did that. But there's also other theories out there about multiverses and things like that. What do you think about this idea of us being, or our universe being one of many that come in and out of existence out of nothing? I mean, we've seen in quantum mechanics subatomic particles. I think it's quarks, or come in and out.
I don't know, all virtual particles of
virtual
all
particles
types
and
are
all
feasible
types.
depending on the
Yeah.
energy that you have available. Right.
So what do you think about multiverses?
Well, there's no evidence for that, by
Sure.
the way. There is absolutely no evidence,
Mm-hmm.
and that really is, mathematically been presented by the string theory community.
Sure.
And they do present where the entire universe, which is made up of many little universes in a sense, is called the bulk, and each individual universe is like a slice of bread within that loaf of bread, which is the entire universe. And they also have a way of even creating in a sense, a slice from that whole loaf, which is basically when two of the M brains, they're called brains, B-R-A-N-E, not a brain, just B-R-A-N-E. And when two brains come together, they can create basically a hole, sort of like the opposite of a black hole, that then releases an entire universe.
Yeah.
But again, that is, there's no evidence that we have for that at this point.
Right.
The best we can do right now is going back to, as I had stated earlier, about
Right.
10 to the minus 40th seconds after the formation of the Big Bang. And our standard model that has been proven and validated cannot go back any further than that.
No, as you point out, this is highly speculative. There's no evidence whatsoever for it. But,
Yeah, for the bulk or the brains
Right.
And
Yeah.
the like, right.
But in this, I believe it was the second episode of Cosmos, the new one, he used a visualization where he's showing the galaxy clusters, the superclusters, appear to be on filaments. And when you back off far enough, it looks like a sponge, for lack of anything else. I mean, it's just, there's so much matter out there, and just myriad of these filaments going everywhere. But further, they backed off further, and this was more or less encapsulated in a finite space. And here's another one, and thousands of others of these. It's kind of a romantic notion, but there's no evidence whatsoever.
No, there's no evidence, and there's no way of getting information
No, it's
from one
permanently-
universe to another. String theory allows, in fact, if we could modulate gravitons, that is one way that you might get some information from one universe to another within the bulk.
Sure.
But again, that's obviously we have no direct evidence, and then to have to go the extra step of modulating a gravitational wave so that you might use that. Because in string theory, gravity is so weak because it's a different type of string.
Right.
And I didn't come with any visualizations for this, but in my cosmology course, I talk about the different types of strings, where all the other forces are stronger in this universe.
Right.
But the gravitational force is actually able, or gravitons theoretically are able to go from one multiverse to another, one universe to another within the multiverse.
That's an interesting.
Once we do learn to modulate gravitons, it's only a few short steps till we get our anti-gravity belts, and that's what I'm waiting for. Sport orbiting, with a belt and a helmet.
I'm afraid that this just doesn't work that way. If
It
you
doesn't?
follow Einstein's general theory of relativity, you're
don't
not
tell
going
me.
to have that kind of anti-gravity effect.
Well, as far as we know, I'm holding out for that.
Yeah.
It's my dream.
So let's. I want to talk a little bit about science education. I mean, you're a professor at George Mason, and you teach science, and you've been writing these books for the general public. And I do believe that the general public, in general, is scientifically not very literate. And I think it's important for professors and researchers to engage the public, such as you're doing with these books, such as Neil deGrasse Tyson is doing with Cosmos. So, in speaking of Cosmos, I've also been hearing some criticisms from some people about that, as it's kind of, as you mentioned, also too cartoonish. It's kind of almost, dumbed down, and my opinion on that is that, well, you kind of, and I don't like to use the word dumb down, but to make it relatable to people, right? And that's a very difficult thing to do, because how do you explain, again, string theory or quantum mechanics or even the theory of relativity to people who may not really have the kind of intellectual grasp, to understand these concepts.
Yeah, there's a lot there. First, I want to say I wasn't saying that Tyson dumbed down Cosmos too much. That was other people who have been saying about that.
Yeah.
And and I'm certainly aware. I mean, just earlier this month, it was. Early this month is a Read Across America Day, and I actually took the opportunity to read in an elementary school classroom. And you have to give them concepts that they can grasp.
Yeah.
Now the situation that we're seeing is there is a significant amount of science illiteracy in the community. And how do you get across these concepts about an expanding universe, about something from nothing, about energy versus matter? There's a lot of concepts to get across. And of course, through science education, we're trying to do that. Now, I'm also a co-investigator of a grant that's at George Mason University in the Graduate School of Education, and the program is called VISTA. And it's the Virginia Initiative for Science Teachers Achievement, and trying to provide professional development for teachers, where we bring them in the summer and have a workshop and explain the science behind it. Because many of these elementary school teachers, I've been dealing with middle school teachers, but elementary school teachers in particular don't have the science background.
Right.
And you have to get them up to snuff about the science. So, we're trying to get efforts going there. We do also see in our classrooms, and I can tell you there was a biologist that just sent me an email a couple of weeks ago about where he was talking about the nature of the environment in some place, and there were students who brought up, it says in the Bible such and such, and it says, science is evidence-based, and that's what we're dealing with. Okay,
Exactly.
So you have to have evidence. And when I give homework assignments, I try to get across to my students, for everything they state, they've got to have a reference to a peer-reviewed paper to give. And so getting this point across of, the difference from science and faith, and just looking where science is evidence-based.
Right.
And when you get outside of that, we're not saying what's true or not and what you believe, but this is the body of facts that we deal with in science.
Right.
We have to work with.
And that's actually part of the issue where we're seeing today a lot of the creationists or the fundamentalist Christians who, they say they want equal time teaching the controversy. These are all theories.
What? Let's.
Yeah.
I want to talk about that in depth. Let's do that after the break. We got to take a couple of more minutes here. So, Paul.
Gosh, Darlene, it sure is amazing how much we have in common.
I know, Larry. We both love three-car pileups. We both were built in Buffalo.
And we both know wearing safety belts helps save thousands of lives.
Yeah, this is fascinating.
Don't mind Vince. He's getting over a bad breakup.
I know. Janet's picking up the pieces, too. They're in here.
I wish they understood it's all worth it to get people to buckle up.
Hey, lacerated lovebirds, I sense a major crush.
You could learn a lot from a dummy. Buckle your safety belt.
Talk about head over heels.
Rosita, did you know there's a right way to sneeze? Let's show them, Elmo. Yeah, got it. When you feel like your nose needs to give it at you, this is how you act. This is what you do. Lift your arm up high, bend it toward your face. Sneeze right there under bendy place. Achoo! You can do it with ease. Achoo! That's the right way to sneeze. Thank you.
To learn more about preventing flu, visit flu.gov.
7,000 high school students drop out every school day. That's a line of desks more than 4 miles long. We can keep students in school. Visit boostUp.org and take the first step.
So, I just moved in with this family, and it's embarrassing. The little one, he likes to go outside and crawl around in the giant litter box. I don't know what he's doing. I mean, I was born and I knew how to use the litter box. Look at that. That's disgusting. Oh, poop already. You're making me nervous. Oh, okay, I can't look at this anymore. I really hope he grows out of this, for his sake.
Be that person.
Be that person.
We're back. The tie. Let's get a good shot of that tie. That's, I don't know if we can get it. We can't get a close up really.
Okay.
But, yeah.
That appears to be deep field stuff with planets.
Well, it's a combination of things.
Yeah.
Of course, it's very artistic rendering. There's the Andromeda Galaxy here, Jupiter, Saturn, some other galaxies, a comet, and the like. I actually got this tie at a meeting of the American Association of Physics Teachers, and I have a couple of dozen of these theme ties that I wear, both physics and astronomy, and sort of gotten known as the guy with the ties at the university.
Yeah. Neil deGrasse Tyson, I saw recently had one with a Saturn V rocket on it. It was just a beauty.
Right. So,
Nevertheless.
Yeah. So we were talking about
creationist pushback.
Yeah, creationist pushback, and one of the things that we're hearing about Cosmos also is there's been an uproar, well, maybe not an uproar, but some complaining that, well, it's not fair to give creationists equal time. Now, as you mentioned, science is fact-based, and Cosmos...
Well, we say evidence.
I mean, evidence-based.
Science
right.
is evidence-based.
That's what I mean, yeah.
And that's...
Sure, evidence-based. So this whole idea of teaching a controversy, like everything's just a theory, can you explain to our audience what exactly a scientific theory is versus what the
scientific method?
Yeah.
Well, the scientific theory is part of the scientific method,
Right.
but a scientific theory is not something that is really in question. You talk about the theory of relativity. We've been demonstrating that Einstein's special theory of relativity and his general theory of relativity have gone through many tests over the years and have been demonstrated to hold valid. And so within the scientific method, which, by the way, now they're changing the terminology if you're not aware of the next generation science standards. They don't like the term scientific method. They want to go to the process of doing science.
Sure.
So within the process of doing science, first you make observations about the world and try to generalize what's going on in the world based upon what you see. And then you test your hypothesis, and ultimately you refine it. It's not a linear process, it's a reiterative process. You go back again and again, refining it and refining it. For example, even with Einstein's theory of relativity, they say, well, it threw away Newton's view of gravity. That's really not true.
Sure.
In one sense, Einstein's general theory of relativity encompasses and includes the Newtonian theory of gravity, but Newton's theory doesn't go far enough in a sense. So Newton's laws of motion were not applicable when you're dealing with velocities approaching the speed of light. And Newton's theory of gravity doesn't work when you're dealing with things that are very massive. So on day-to-day purpose, and even within the solar system, they were predicting the orbits of planets using Newton. The most famous one, the first one, of course, was Halley's Comet, which had a not-so-great apparition in 1986, but I was able to see it out from Shenandoah National Park.
Very cool.
But, again, knowing that returns every 76 years, it's able to be done just within Newton. But there were things that Newton's gravity didn't predict and we couldn't understand, such as what's called the precession of the orbit of Mercury. That it actually was not completely stable, it precesses. And Newton's theories of gravity could not explain it. But within Einstein's general theory of gravity, general theory of relativity, which encompasses gravity, he was able to explain the precession of the orbit of Mercury and then make other predictions. And that's the stalwart of an actual theory that you're putting forward, that you make predictions as well as you explain observations that are already made and have a way to validate it, or more so to prove that it's wrong. And when you're dealing with a number of these so-called creation theories, there's no one theory there, and there's no way to prove them wrong.
Well, they're not actually true theories.
Falsifiability
is within the scientific process. They are not theories. They are just trying to explain that which our science maybe doesn't explain.
Right. And one of the things I want to mention is that within the process of doing science, the scientific method is, as you said, predictability is the number one key. And creationists cannot predict anything, And also, the way science works is, as you said, you make general observations, you make a hypothesis, you think, okay, this is what's going on, let me do some experiments, and then that's why you have a null hypothesis, right? You're actually working to falsify your claim.
Right.
And if you fail to falsify your claim, that means the claim has to be true.
Or
right?
if there's no way to falsify it, like the existence of a supreme deity.
Right. Well, that's the thing. That's not science, and that's what I think. There's so
no way
much
to test
confusion.
that
There's no way
within
to test
science.
it, and it can't be falsified one way or another. But also, more importantly, I think, is that a lot of creationists already have a conclusion, and now they're trying to find evidence for that conclusion, and that's not how science works.
Yeah.
You don't start with a conclusion, which that's
and
what
then
they
cherry
do.
pick
and then
your-
cherry
Well-
pick the science that fits.
Well, some people
you
do,
know.
and that's called an ad hoc theory. I mean,
Right.
you're just trying to find the stuff that explains what you want and not apply it in general.
The actual meaning of theory is widely misunderstood on the religious side, the creationist side. They think it's basically a wild guess, which is probably
Right.
wrong. Like saying,
Right.
I have a theory why women act like that. Well, you don't have a theory.
Yeah, that's really a hypothesis.
Yeah.
Yeah, hypothesis.
That's a
right.
hypothesis.
I have a
It's not
hypothesis why women act
theory.
like that. would
Theory
be
of
the right way to say
relativity.
it.
And then when we don't use this terminology as much anymore, but when theories have been proven over a long period of time, then they refer to them as laws.
Laws,
Because originally it was Newton's theory of motion and everything. But I mean, this has been held for so long, centuries now, that it's the law of
The
motion,
law of motion,
the law
right.
of
That
gravitational
it's pretty much
attraction.
inconceivable that something could come along now to contradict that.
Right.
And
Well, I mean, then you get into the thing. Well, Einstein came up with the general theory of relativity, which went beyond. Again, Newton's law of gravitational attraction is not questioned within Einstein, but Newton couldn't handle the more massive stuff and things that happen in space-time that, very massive. And
But
by
as
very
far as-
massive, I mean, massive stars.
Yeah.
So he,
But as far as it applies to our gravitational well that we're in here with the sun,
yeah, there's nothing
planets,
that is
right. Goes nowhere
That's
near-
why Newton's law of gravity is called the law of
Right.
gravity, because it's been demonstrated valid for so many centuries.
And more importantly, a scientific theory is a set of facts within, that theory. So
It's a set of demonstrated evidence,
right.
And all of that evidence holds together to support the theory.
right.
So yes, it's very different than what people say, and even my students say, well, that's just a theory. Or
Just
like,
a theory, right.
No, just, well, what you really mean is it's just a hypothesis, but what we're talking about is a theory which already has a body of evidence support. If I may say, the theory of evolution.
Sure.
It's really a fact that things have evolved. And if you don't want to believe that, you can even look to modern day with what has happened with microbes. And microbes evolve much quicker. One of the reasons people have problems with evolution, I think, is because it's over such a long period of time.
They can't quite
We
grasp that
only live, if we're lucky, to be like 100 years at most. And we don't see this flow of evolution.
Right.
But when you're dealing with microbes and bacteria, and particularly viruses, we can see how they evolve over time in a much shorter period of time. And so that's something that can be shown as evidence of evolution.
right. Like the trilobite fossils you have in your pocket that you showed me, there are those. And Tiktaalik, these are a record of things past. These are not just inventions or anything.
Right.
These are a record of things that have, I don't know if you can even see it, but that's a,
Probably can. It's very small.
yeah, it's a trilobite. This is a thing that lived
Yeah.
550 million years
500
ago.
million years.
Yeah, 500 million
That's
years
what
ago.
it is. 500
Tiktaalik
million
was
years found in
discovered to be in sediment 375 million years old, exactly as predicted.
Right.
That was when they had pretty much narrowed it down when it had to be.
Yeah, that's another trilobite.
Once the dominant species on the planet, apparently.
That's right.
Yeah.
At one point.
Every-
And you do have to,
ocean.
they dominated for millions of
Yeah.
years, and I wonder if humans will last as long.
But-
And just as these rocks are 500 million years, and there are methods by which we can demonstrate
Sure.
this.
Sure.
This is a meteorite, and this little rock is 4.5 billion years, and there are ways that we can demonstrate its age.
So what are one of those? What is one of the ways you can demonstrate?
Radiometric dating, that is the radioactive decay of the
Which is a
chemical
favorite
species.
target of the creationists. They just basically deny all these forms of radiometric dating are valid. You know, because they may find a problem with one of them, like carbon-14 or something, and they extrapolate that across all the processes.
Actually, carbon wouldn't work for this
No,
kind
of course.
because it doesn't have as long a half-life.
But
right?
but they'll point to
overlook the fact that there
problems.
are other radionuclides that we use
Absolutely.
to date these rocks.
But it's
and you
key
would
to
have
their
to say that
argument.
it's just not one radioactive decay process that we don't understand, but all of them. And we've just been doing this for so long, and it has been demonstrated for rocks from space like this meteorite and rocks from the moon.
But it is characteristic of their argument is that they need to deny all radiometric dating systems.
Right,
processes.
and they're just plain wrong when they
And they're
deny
just
that.
wrong.
They just don't quite understand.
Well, there's
that
just no
concept,
evidence
yeah.
to support that.
No. And that's why they're not really doing science.
That's correct.
And that's why it's ludicrous when they demand equal time on Cosmos.
Right.
Of course, Comedy Central has offered them a slot.
Well, the thing about equal time that I have a problem with is, first of all, Cosmos is a series that is produced privately, done privately.
Right. Yeah. Exactly.
And there's not just one alternative to the views presented by Tyson on Cosmos. You know, there are people who still follow the steady state model of the universe. There's not really many of them, but there are some scientists that still try to hold to that. So would you have to give all of those? And Tyson has also made reference to some theories that there are many alternatives.
Sure.
And so you're going to have all of those alternatives. It just doesn't.
Yeah, that doesn't make any sense. Correct.
Dr. Geller, we're going to need to cut you off there. We appreciate you coming in. Dr. Harold Geller, the Observatory Director at George Mason University and Associate Professor at the Physics, Astronomy, and Computational Sciences Department at George Mason. Thank you so much for being with us today and enlightening us on this. We try to keep people up to date with science here, and of course now we're totally up to date on science. So
well, one part of science.
We'll check in a year or so and see. And
but it was a pleasure having you on the show.
And
so next week, do we? Oh, the book. His book,
Dr. Geller's book, and the new one is called
All the Secrets of the Universe in large print.
Okay, in large print.
And that will cover some of the material that we talked about here too.
Okay.
All right. Well, thanks for joining us, and we will see you next week. Do we have a guest?
I'm not sure who yet, but we will.
Okay. Thank you much.
Oops.